So I'm going to start with a little story. So you walk into a car dealership and you say to the salesperson, if I buy this car, if I pay for it, will you give me the keys? And the salesperson probably looks at you and says, yeah, of course I'll give you the keys once you pay. So you negotiate a price, you pay the man, and they hand you the physical keys. And you're like, well, that's not what I meant. I want the master ECU key. And by the end of this talk, you'll know what that is. So you leave, you're a little sad, and then maybe you think to yourself, well, maybe the keys are in the car somewhere. Maybe they're hidden. And maybe I can find them. And so this talk is about the search for those keys. So newer vehicles started using cryptography to sign messages on the CAN bus. This prevents third-party devices from also trying to send those same messages easily. In this talk, we're going to do an intro to car hacking, explain the encryption standards used for the one that we targeted, and how we ultimately managed to extract the keys over the CAN bus for at least an ECU in one vehicle. Specifically, we were interested in extracting keys used to sign messages that control steer-by-wire. Also, we just wanted to prove some people wrong on the internet. This person here on Reddit, for example, is claiming that the OEM security is so good that it's going to be impossible for someone to get around it. My name is Greg Hogan. I work on infrastructure at Comma AI. That's like servers and data center. So my professional job is really nothing to do with car hacking. Car hacking is my hobby. I spend a lot of time reverse engineering automotive firmware on my free time. And this project was one of those things I worked on.
So I'm Willem. We started this research when we were still colleagues, also mostly a hobby. And then I like car hacking stuff so much, I decided to start my own company doing it. So I do like pen testing, consulting, fuzzing, and like trainings, like the one at hardwear.io this week.
All right, so let's get started. So what got us started on this? A little more about that. If you're not familiar with OpenPilot, it's an open source aftermarket driver assistance system. It's similar to Tesla Autopilot, but for non-Tesla vehicles. Vehicles that shipped with the ability to control steering by wire and the gas and brakes over the CAN bus. The OEM camera module generally sends the steer-by-wire messages to control. It sends those messages over the CAN bus to the power steering motor. And so for OpenPilot support, you need to be able to essentially send those same messages on the CAN bus. So some new cars started showing up where the previous models were supported and a new model year was not. It was noticed very quickly that some of the CAN message format had changed, some of the messages, the format had changed on the CAN bus, and then quickly discovered that what had changed was some new security measures had been put in place, specifically SecOC, which adds a cryptographic signature to CAN messages. On the right here, you can see an example of such a CAN message. It's a steer-by-wire control CAN message where the first 32 bits is the actual payload, and the last 32 bits is related to the cryptographic signature. So these vehicles started showing up around 2020, at least that's when we noticed them. A couple of years later, we bought a power steering ECU for one of those vehicles. A few months later, we were able to obtain the firmware, and then a few months after that, we managed to find a way to extract the keys over the CAN bus.
So hopefully at the end of the day, you also walk away with some knowledge about car hacking. So we'll quickly do a Automotive 101. We'll go through this very quickly. So we'll start with CAN bus. So CAN bus is the most common network used in vehicles for ECUs to communicate. It's quite an old standard. It was introduced in 1986 and first used in 91 for production cars. Basically, CAN bus is a very robust but slow network. Typically runs at like 500 kilobits, and you have up to 8 bytes of payload, which kind of drives a lot of the engineering decisions down the line for this cryptography stuff. There's some newer standards called CANFD that allow more payload and slightly faster data rates, but this was not used on this car in this specific research. CAN bus has no guarantees on timing due to the way how arbitration works. It can actually take quite a while for a message to be sent if the bus load is high. And because there's no guarantees on timing, this makes it pretty trivial to do man-in-the-middle attacks. Receive a message, make some changes, and then send it back on the bus. A typical topology is where a car has multiple CAN buses tied together by a gateway. And this gateway is also connected to the OBD2 port for diagnostic stuff, and that protects the regular CAN traffic from the outside. Then also briefly talk about UDS. UDS is an ISO standard used for diagnostic communication. Basically every ECU in your car will support this, and has very nice primitives for car hacking. And if you start looking at a new ECU, you just start talking UDS to it. It's used in the workshop for flashing updates, and also to do things like reading trouble codes or testing stuff. So UDS request contains of a service ID, followed by an optional subfunction ID and a payload. And then the response from the ECU will respond with the service ID plus hex 40 and some payload as well. And there's also standardized error codes, something like format is wrong or needs authentication. Some primitives we'll be using in this research is UDS SID10 diagnostic session control, which is used normally an ECU is in a default session. You can go into extended diagnostics if you want to change like configuration, or if you want to reflash an ECU, you go into the programming session, which usually jumps into some bootloader. Another primitive is read memory by address, where it will allow us to read certain ranges. Usually this is disabled or very heavily limited to certain places. Then there's also security access, which is the normal way to authenticate a tester to an ECU. It's a challenge response-based system where you press a seed, you do some cryptographic operation on them. Sometimes this is very simple XOR, or sometimes it's more advanced. And then you set back the key that you computed, which will be verified by the ECU. On newer cars, there's also some certificate-based infrastructure, but I haven't actually seen this yet. And then there's also routine control, which is kind of a remote procedure car on a car. You can start a routine with a certain ID, and you can start, stop it, or get the results. And this is used for things like erasing flash or asking the ECU to compute a checksum. Flashing is done using request download. So we request the ECU to flash some firmware to a certain place in flash with a certain size. And then we use SID36 to actually transfer blocks of data. So now Greg will talk a little bit about how these firmware updates work.
So this is kind of the typical memory layout, the address space layout of these microcontrollers. There's a bootloader application code, and then some vehicle-specific, maybe calibration data. So far, I've never seen one that actually does like a true signature check on the firmware every boot. Probably because it'd be too slow. Like your power steering motor needs to get powered on and start assisting instantly. So the way that the firmware update process commonly works is, well, first of all, the ECU powers on and it goes into the bootloader. The bootloader then does some checks and says, okay, there's an application, jumps into the application code. Now I'm going to request a programming session over UDS, which is going to cause it to jump back to the bootloader a lot of the time. You then issue a routine control call to erase the application flash. And then you use the request download and transfer data to tell it what address range you want to flash and actually send the data that you want to write to flash. At the end, you generally call another routine control called check programming dependencies, which The good ones do something like internally compute a checksum, and then you verify that the checksum that comes back is the checksum of the software that you thought you sent to the ECU. And then I guess one last note is at the very end, it commonly writes out some flag somewhere in Flash saying there's good application code here now. So if this failed at any point in the process, you power cycle the ECU, you're still in the bootloader, or you're in the bootloader when it fires up, and then it checks for that flag. It says it's not there, and then you still are in this bootloader that allows flashing. If you mess something up, if everything went successfully, then that's the flag that gets checked at the beginning as to whether or not to jump into the application code. Reverse engineering automotive firmware. I'm just going to go over some high-level basics here. Automotive microcontrollers commonly have three architectures. We see PowerPC, V850, and Tri-Core. These microcontrollers you generally don't see in consumer electronics because things like power steering motors have are very safety critical devices. So they have these certifications like ASIL that makes them generally more expensive, and for some reason they commonly seem to be less resistant to modern attacks like fault injection. When I get started on a new ECU, something that I commonly do is check for pads that are for JTAG or some proprietary UART, and then you can commonly download from the microcontroller manufacturer's website some software that allows you to easily interface with that debug port. If you're really lucky, they didn't lock the debug port, which is becoming less and less common these days. If you manage to obtain the code, I always use Ghidra now to try to find the things I'm looking for. It has pretty good support for automotive microcontrollers. You want to tweak some settings a lot of the time. When you start out, you're going to run the automatic analysis. Like something I always do is turn off address table searching because it'll inevitably throw address tables in the middle of code. Once you've run the automatic analysis, you commonly have to then find more code that was missed. The reason for this is because this automotive firmware format, it generally doesn't have any sort of header that says like this section is code and this section is data and so forth. So a good strategy for finding the rest of the code is to look in Ghidra at this entropy map. And so you can see here in the diagram, black is all zeros, which obviously isn't code. And the entropy map shows like a blue color where there's code. So you just kind of go through and try to manually disassemble anything that was missed. One of the first things I'm always looking for are diagnostic protocol handlers in the firmware. A couple really common diagnostic protocols are XCP and CCP. These, if they're present, they often have read and write memory by address just wide open. A good way to find them is to look in the code for functions that return multiple error codes that match up with the protocol. So like here, for example, you can see it's returning in one branch, 22 and another in 28. So this is most likely, 29. Yeah. So this one's most likely a XCP handler. UDS handlers are good to look for also. Same strategy to find them. And you want to check if there's read and write memory by address, just in case they left that open for you. Another good place to start is to look at the datasheet and find the CAN registers. You're almost always looking for information related to CAN messages, and a good place to start is where the data is extracted from the CAN registers. Automotive firmware uses tons of global variables. I guess it is a side effect of how debugging works for these microcontrollers. I think a lot of the software used for developing, like if you want to inspect like the state of things in a running system, you'll have some file that you load that has a map of like addresses to like specifically named state variables and so forth. So spend a lot of time labeling global variables. Another thing that aids in reverse engineering is mapping out large structs that exist in these global variable address space. Basically, it's not uncommon that with some of the more complicated automotive firmware libraries that are used, that you'll find some interesting piece of data, you know what it is, and it'll just have a read address reference to it. And you're like, well, where the heck was it written to? You go back through the address space to lower address numbers, and then you may find something like this upper right-hand corner here, where it's doing like a mem copy. So if you turn that whole region into a struct, then all of a sudden you're going to have address references in Ghidra that you can follow backwards recursively and aid you in tracking down the true source of that data. The CAN parsing is another thing to dig into. So it's not uncommon for it to be table-based, where there's a configuration table that has all the signals, which is like some portion of a single CAN message. It'll essentially be like, here's a function handler for this CAN message, and to parse it, and you want to extract bits 4 through 6, and you need to shift it 5 bits to have the value. You may also find some explicit code that does CAN parsing, where you'll see, the shifting and the masking in the code, as opposed to like some generic function that executes that operation based on a table. Sometimes it's not super easy to find things you're looking for in Ghidra, and you'd really like to be able to search the code in your favorite IDE. A good way to do that is to export the program to C or C++ in Ghidra, and then you can write like a regex. For example, this message here, I was looking for like things building CAN messages, so I write a regex that looks for shifting and masking and bitwise ORing multiple times all in the same line to quickly find things like that. Another common thing that's used in automotive firmware is something called AutoSAR. It's an open source specification with closed source implementation. There's a bunch of different layers. It's fairly complicated. You can spend a lot of time reading about it. Some people like to describe it as an entire Italian restaurant worth of spaghetti code. It's definitely a lot of auto-generated code. Parts of it are like the hardware abstraction layer will be implemented by the automotive manufacturer, or the microcontroller manufacturer. Someone else will make the runtime, and then the automotive manufacturers might be implementing the pieces in the middle that tie everything together. It basically specifies an API that's supposed to be common no matter what microcontroller you're running on. So I guess the promise is that you write your code and it's super interoperable, but I kind of have my doubts that it's ever that simple. All right, so let's talk about SecOC. This is the cryptographic signature that's used in these messages that we were interested in. This is an AutoSAR standard, and it replaces the traditional method of checksums on CAN messages, which is commonly that you use like 8 bits for a CRC8 or some simple XOR operation. Obviously, cryptographic signatures are going to be a lot better. So, what is SecOC? As I mentioned, it's an AutoSAR standard. Their goal is to add cryptographic signatures. The standard specifies AES is used for the cryptographic signatures. It's supposed to be low overhead so that it can run on low power microcontrollers and protect you from replay attacks and has rollback protection and so forth. So here's an example of how the signing process of a CAN message works. There's a few important components here. There's a secret symmetric key that the sender will have. There's a payload, which is the actual message that you want to transmit, the data you want to transmit on CAN. And then there's a freshness value, which is a bunch of counters that is for the rollback protection. So the sender then generates a cryptographic signature on this payload. It then puts into a CAN message the payload plus a portion of the counter and a portion of the cryptographic signature. The receiver can then take that information, use the counters for synchronization purposes, and see if it can compute the same cryptographic signature and decide whether or not it trusts the message is valid. So the counter part of it that I mentioned is the freshness value. It consists of multiple counters. The first one is a trip counter that is supposed to increment every time the ECU powers on. There's also a message counter that increments every time you send a message. There's a reset counter. This is just periodically incremented for synchronization purposes. And then you take that, in this example here, it's 48 bits, and we're going to truncate it down to just 4 bits that we transmit on the CAN bus. The receiving side is going to have its own internal counters that match, and it's just going to use these 4 bits to try to keep track of where it's at and how these counters progress without actually having the full values. The cryptographic signature that's sent on the CAN bus, it consists of the CAN address, the message ID, the payload, and the freshness value. You take that data and you generate 128-bit AES cryptographic signature. You then 128 bits, like a lot of CAN bus messages are only 64 bits, so obviously you can't put the entire signature in the message, so they truncate it to, in this example here, 28 bits. And what you do is you put the payload along with those 28 bits on the CAN bus. So here's an example of that secure CAN message, just like I described it. So how are the keys managed that are used to sign these cryptographic messages? This is in the secure hardware extension specification of SecOC. There's a whole bunch of keys, and they all have very specific roles, and the specification defines what those keys should each be used for. The ones that we're really interested in here is the master ECU key. That is a key that allows you to change the keys, to rotate the keys. And then keys 1 through 10 are generally the keys used to sign the cryptographic messages. So how do we set the keys? That's done through the key update procedure, which is also in the AutoStar spec. The keys are not transmitted in plain text. So as an example here, let's say a vehicle manufacturer is going to implement this. They're going to generate a key for probably every VIN number or every VIN number and serial number of every ECU in every vehicle they manufacture, and they're going to hold that in a private database. They're probably going to set up some HTTP API that you can call and say, like, here's my VIN and here's my serial number for my ECU. It will then generate a new key for you if that's the request you're making, and increment a counter and encrypt that key with the master key. That information is placed into these values here we call M1 through M5. The device on the other side that's actually plugged into the car that's going to assign the key or write the key into the car then receives M1, 2, 3, M4 and 5 are something that's generated from the new key. And then you can verify that, so that way you can verify that the key is actually from a trusted source. So M2 is the one that we're really interested in here. M2 actually has the encrypted new key, but because the way it works is you use the master key or some other known key to the ECU to encrypt this key, if you get a hold of M2, it doesn't really matter because you don't have the keys that were used to encrypt the new key. And ideally, every vehicle has different keys. There's also a counter in here which prevents things like replay attacks. So here's an example of a log, for example, from an automotive manufacturer's application software that gets dropped as part of the rekeying process. And as you can see, M2 is in here, which you know has the key that you're looking for, but unfortunately you have no way to get the key out of it.
Cool. So now that we have all the theory out of the way and everyone knows what we're dealing with, we'll start on our actual attack. So this is the specific target we chose. So in our research, we decided to just tackle one car model first, and then later see if we could branch out to other cars. For this specific car, we had to choose an ECU that would be the most promising. So in this case, we decided to attack the power steering ECU, which we know it was checking the messages that we're interested in. And it will also use an SLD microcontroller, which we hoped had less mitigations against things like fault injection. So we bought an ECU, we took it apart, and then we got to our target, which contains an RH850. Unfortunately, the JTAG was locked, but we used a fault injection attack to get access to this, which was based on some research on another chip from a different family. So basically it has a UART protocol that you can use to read and write flash. You can set a fuse to disable it, but what happens is it's not actually disabled. So you can still send commands to like set the baud rate, and then you go through some commands, and then you say, okay, well, synchronize now, so actually connect. And then the chip will tell you, no, sorry, I can't do that because I'm locked. Or JTAG is not actually enabled. So we decided that this was a good point to do some fault injection. So yeah, this chip has internal regulators for the core voltage. It's like a 1.25 volt regulator, which is brought out to some capacitors for stabilization, which we thought was a good point for doing our fault injection. So we have our glitch setup. We removed the bypass capacitors. This chip actually has 2 cores, so we just decided to glitch both core voltages at the same time by just putting 2 NFETs on the board. And then we have this is what our glitch look like. Might not be the prettiest glitch shape, but it did the trick. And also we did this with a Raspberry Pi Pico. So we did this with like less than $10 in hardware cost. If you don't include that Sele that's in the back there. So we had the Pico connected to the PC to set some like glitch width parameters, and then on the PC side we talked to the protocol, and then later we also replicated this with Chip Whisperer Husky, if that's what you have, and the code for this is on GitHub. So this is kind of what it looks like. So this is the last byte of the synchronize command, and then we inject our glitch. And then we get a positive response back, and then we get full access to the rest of the protocol so we can dump the firmware. So now we have the firmware. Now we can do some reverse engineering.
Okay, so the first thing that we do is we start looking at the application code in the firmware. And the first thing we wanted to verify was that if you look at the network topology of this vehicle, the camera module is sending the messages that we're interested in, and the power steering motor module is behind a gateway, there's a gateway between them. So we wanted to make sure that we weren't overcomplicating this, and confirmed that yes, in fact, the gateway is not the one doing the SecOC signature validation. The power steering motor is actually the one doing it, which was the case. So we started just kind of our general audit of the code, looking for the common things that we're looking for, like XCP implementation, CCP implementation, because we don't want to have to tear apart another ECU to reproduce this on another target. We didn't find either of those. UDS did have read memory by address, but it was locked down. The ranges of RAM, for example, that had the keys did not allow read memory by address. So the SecOC implementation here didn't seem to have any major flaws at all. We did find that all the key management stuff was all implemented in code, but our general audit didn't turn up anything that made it super easy. As I mentioned, the cryptographic keys were in RAM. The HSM was not used if this ECU had one. And so we did have the keys at this point for the specific ECU that we were looking at, although we did try to use these keys to then sign messages for other vehicles and quickly discovered that, at least by VIN number, they had used different keys. So the keys that we had were good for the ECU that we had. We could now generate messages that it would accept, but we could not generate messages for other vehicles. Changing the signing key, we also had a master ECU key that would allow us to change the keys in this ECU. But again, the master key was specific to the VIN number at least, so this master key didn't get us anything on any other vehicles. Also, we found several ways to change the master keys, but again, they were all well secured. Another thing we looked at was if there was some way to disable the SecOC validation in the ECU, in the firmware. We did find that for about 1 second after the ECU turns on, it ignores, it skips SecOC validation. This is probably to manage like synchronization when it first powers on, to get the counters in sync and so forth. But we didn't find any way to extend this to a longer period of time. We could patch the firmware and just always have the SecOC validation disabled, but we hope for a better solution than that. A few other interesting things that we found. We didn't really go deep into these because we moved on to the bootloader. But a few other things that were interesting was that we found that the trip counter didn't seem to actually prevent replay attacks. You could reboot the ECU and then give it a trip counter of 0, and it would happily accept messages that were encrypted for that trip counter. There were some UDS handlers that were non-standard that we weren't familiar with, hex AB and BA, but not really sure what those were. But one interesting thing was that we had an ECU that had never been in a car before, so it had never been keyed for a car. But it did have a key that you could use to sign messages with that was all ones. So I suppose if you really were motivated, you could just buy a replacement part and put it in a car. And the rest of the car wouldn't be very happy, but you could send messages that it would accept.
So after we spent a bunch of time analyzing the application and we didn't really find anything, we turned our attention to the bootloader. So we started digging into the UDS routines, specifically the ones used for reflashing the ECU. So what we noticed was it was possible to reflash parts of the flash, but it was also possible to download some code into RAM. And it sounded very promising. And then we also noticed some jumps from some functions into this code in RAM. So then basically started a whole journey to get our code into this place in RAM and get the ECU to execute it. And this turned out to be a lot more difficult than we thought. So yeah, what it probably expects is you to upload some flashing routines when you actually want to update the ECU. The ECU bootloader itself doesn't contain any code handling flash operations. So I'm not exactly sure why they do this, but usually these flashing routines need to run from RAM anyway, so they don't need to relocate them this way. Maybe they were worried about potential bugs in this flashing implementation, so they wanted to be flexible. Or maybe they wanted to implement further decryption steps if they were able to, if they wanted to upload an encrypted firmware. Other ECUs, we've seen this too, but then usually they just upload a whole second stage bootloader that contains like a full UDS implementation. But in this case, they clearly expected to just upload a single function that handles erase or flash operations. Unfortunately, there were no updates for this ECU, so we had no reference to this specific payload. So yeah, we did some more reverse engineering on to see what kind of format of the payload it expects. So it expects like the code to be at the beginning of this payload. So I labeled this shell code here, but this would be your flashing function. Then there's a bunch of hard-coded values. Then there's a CRC32. And then there's also an AES CMAC, which is kind of a signature on this blob. But then it's with a symmetric key, which we of course had access to because we had the full firmware. Well, then, okay, it's signed now, so it's probably secure now. So no, then we also need to encrypt this blob. So we sent the ECU some key material and an IV. And then based on that same AES key, it derives a decryption key, and it uses that to decrypt the blob. But this blob is also decrypted asynchronously in another thread on the RTOS. So it took quite a bit of reverse engineering to figure this all out. But basically, we have a way to construct a payload now. So what we do is we build a cross-compiler first, because we definitely don't want to be writing any assembly today. Then we write some C that basically takes the area of RAM that we're interested in, and it shoves it into the CAN registers, and so we can just see it on the CAN bus. And then when it's done, we call the reset function in the ECU. So it just resumes normal operation. And then we have a Python script which actually builds the payload, takes care of all the AES CMAX and the encryption step. So a summary of findings. We knew that the keys were in RAM, so we just had to find a way to get them out. So what we do is we jump to the bootloader. We go through authentication, which uses a seed key based on some other AES key. Then we send some data to derive the decryption keys for the blob that we're going to send. Then we upload the encrypted blob, and then we call a routine control to trigger an erase. This erase would normally call the function that was uploaded, but instead of like doing an actual erase, which of course we don't want, we trigger our shellcode, dump out the contents, and then reboot the ECU. So we're going to show that now. So we have the actual ECU here. Let's make this a little bigger so we can. So we can see that the ECU is running and it's outputting some CAN traffic. So what we do now is we run our exploit and it's done. So what this does, it checks the firmware version just to make sure we're seeing an expected ECU. Then we jump to the bootloader, check the bootloader version, do security access, upload the IV and the key material, which we just use zeros. We transfer the payload, we execute the payload, and then we dump out the keys. So in conclusion, we got code execution in the bootloader, which, as far as we can tell, is present on a whole bunch of models, basically everything we've seen so far. And then we also have the SecOC key stored in plain text, and that was only found on just 2 models so far. So I guess we still have some more research to do. But in general, this ECU, I think, held up really well to all our attempts. There were a lot of things that didn't work. Like we spent probably over 250 hours of reverse engineering, if not more. So I think they did a pretty good job. I think most of this came down to like a bad specification of using symmetric keys to sign payloads. So we have an exploit POC that's on GitHub, which contains a pre-signed payload to extract this little bit of RAM that contains the keys. So yeah, there's some mitigations in newer ECUs that I think weren't designed during COVID. So now they actually use an HSM for CMAC, so there's no more keys in plain text. But the code execution is still there, so we could do things like patch out the checks, or maybe turn the HSM into a signing oracle for us. But we haven't spent much time on it. Some recommendations that would make our work a lot harder is if you use an HSM and you jump to the bootloader, you could delete all the keys, which would be very annoying for us. Also, something you should do is use a different SecOC key per message and then set up the key permission so that some ECUs can only verify them and other ECUs can only send them. And this would prevent turning an ECU with code execution into a signing oracle. Also implement proper secure boots, which would prevent us from patching anything. And also please use RSA signatures for update files or blobs. Also a quick note about responsible disclosure. Please be like Tesla here, where they expect you to disclose your research after a reasonable amount of time. And especially with hardware stuff where there might not be a solution. I really don't want our research to end up in some SharePoint drive somewhere instead of on a conference. Any questions?
Awesome talk, thank you. Hello. My question is, you gave an example where the 128 byte CAN message, and in one example, there's 100 bytes of the message and then 28 bytes of signature that was truncated. Is that right?
So yeah, you're talking about bits here. We don't have
bits.
that much payload.
Oh, excuse me, bits. So 100 bits of CAN message, and what was left was 28. So that was a truncated signature, right?
Yeah, so the CAN message is 64 bits, and the full signature would be 128 bits, so we can't even fit the whole signature, even if we wanted to.
So could you construct a message where it's a 127-bit message, so there's only one bit left for the signature?
So I'm not exactly sure what your question is, but so we have to truncate this MAC to something reasonable, so we keep space for the payload. And this truncation, like how much bits of of MAC there is in the message, is hard-coded in the firmware.
I see. So that's hard-coded. It doesn't truncate further and further if you have a longer message.
No.
Okay, got it. Thank you.
I guess I have two crypto-related questions. One is, you mentioned asymmetric cryptography. Do you see it feasible to convince the manufacturers of these parts to switch to that, given the extreme sort of performance limitations that lead them to do things like truncate a MAC down to 28 bits?
So I'm no cryptography expert, but from what I understand, if you have an RSA signature, you're not actually able to truncate anything. You need to send the whole signature. So I'm not really sure how you would use RSA signatures if you only have 64 bits of payloads.
I guess the other thing I would say is if you're truncating your CMAC down to 28 bits, why bother? that's like not having anything.
Well, so the thing is, if you want to brute force, like if you only want to get one message through, you have to brute force 28 bits on a bus that's 500 kilobits. So that's probably quite a job. And if you want to do anything reasonable, like inject steering commands, like you don't want just one message to come through. You want a whole bunch of messages with like sequential counters to come through. So then I think 28 bits is plenty of security.
Thanks.
How did you guys bypass the secure access? You initiated secure access, right, for the UDS?
What do you mean, the JTAG or the?
No, the security access. So,
the security access. Yes. Oh, yeah. So that also uses an AES. I didn't want to go into too much detail because of time, but there's a second AES key there. So you request a seed together with some, I think something kind of like an IV, and then it generates some random data, which it encrypts with this AES key, and then it expects you to encrypt this seed as well. But it's also symmetric. So if you have the keys, it's trivial.
Okay, thanks.
Any other questions?
How does the provisioning work? The key provisioning works?
You mean in the factory?
Yeah.
So from what we saw that, we don't know how the ECU master key is loaded, but they probably put that in data flash somewhere. And then when the ECU is new, there's no SecOC key in there. So probably once the car is all assembled together, then they run like the standard rekeying operation. That's also used when you replace a part, and then all the SecOC keys are provisioned.
Yeah, multiple ECUs in the vehicle are going to need the same key. So like if manufacturer A makes the camera and B makes the power steering motor, neither of them will have what they need to start. And then once it goes into a car, you go through that provisioning process is what we've seen.
All right. Any other questions?
That is a great job. Awesome to see.
Yeah. Thank you very much. Really appreciate it. Good job.